Dear students, myself Bonifus here. This one is the first lecture in the lecture series for 06EC7125 Low Power Digital Design for Module 1, which is the elective 5 in your curriculum. We will start with the need for low power VLSI chips. Power dissipation of VLSI chips. It was a neglected subject for quite a long time. In the past, the device density and operating frequency were low enough that it was not a constraining factor in the chips. As the scale of integration improves, more transistors, faster and smaller than their predecessors, are being packed into a chip. This leads to the steady growth of operating frequency and processing capacity per chip, resulting in increased power dissipation. There are various interpretations of the Moore's law that predicts the growth rate of the integrated circuits. One such estimate places the rate at 2 times for every 18 months. Others claim that the device density increases tenfold in every 7 years. Regardless of the exact numbers, everyone agrees that the growth rate is rapid with no signs of slowing down. New generations of processing technology are being developed while present generation devices are at a very safe distance from the fundamental physical limits. A need for low power VLSI chips arises from such evolution forces of integration circuits. Another factor that fuels the need for low power chips is the increased market demand for portable consumer electronics powered by batteries. The carving for smaller, lighter, and more durable electronic products indirectly translates to low power requirements. Battery life is becoming a product differentiator in many portable electronic markets. Being the heaviest and biggest component in many portable systems, batteries have not experienced the similar rapid density growth compared to electronic circuits. The specific weight, that is the stored energy per unit weight of batteries, barely doubles in several years. Besides technological issues, further increase in battery specific weight will soon draw safety concerns because the energy density is approaching that of explosive chemicals. It has been generally concluded that battery technology alone will not solve the low power problem in the near future. Ironically, high performance computing system characterized by large power dissipation also drives the low power needs. The power dissipation of high-performance microprocessors is now approaching several dozen watts, comparable to that of a handheld soldering iron. Power dissipation has a direct impact on the packaging cost of the chip and the cooling cost of the system. Some personal computer CPU require cooling fans directly mounted on the chip carriers due to high power dissipation. A chip that operates at 3.3 volt, consuming 10 watt means that the average current is 3 ampere. The transient current could be several times larger than the average current. This creates a problem in the design of power supply rails and poses big challenges in the analysis of digital noise immunity. Another major demand for low power chips and systems comes from the environmental concerns. Modern offices are now furnished with office automation equipment that consume large amount of power. Computers are the fastest growing electricity loads in the commercial sector. Since electricity generation is a major source of air pollution, inefficient energy usage in computing equipment indirectly contributes to environmental pollution. Many of the countries have started energy saving star programs to promote the sales of energy efficient electronic equipments. So we have seen the needs for low power VLSI chips, which can be summarized as device density and operating frequency, Moore's law, increased market demand for portable consumer electronics provided by battery, high performance computing system, and environmental concerns. Now, in this subject, we will be dealing with what are the sources of this power consumption inside a VLSI chip, or what are the physical mechanisms, how we can analyze it, how we can simulate those power dissipation, how we can reduce, what all the techniques can be used, what other techniques are being used in industry. So all those things we will be covering in this particular subject. So the next topic is sources of dissipation in digital integrated circuits. The main sources of dissipation in digital integrated circuits are static power and dynamic power. So first we will focus on static power. Ideally, CMOS circuits dissipate no static DC power, since in the steady state there is no direct path from VDD rail to ground rail. Thus, ideally, at a time, PMOS and NMOS won't be turned simultaneously, ideally. But MOS transistor is not a perfect switch. There will always be leakage currents, and substrate injection currents lead to static component of CMOS power dissipation. Assume that we are having an NMOS device with W by L ratio 10 by 0.5. Then for such device, the substrate injection current will be in the order of 1 to 100 microampere for a VDD max of 5 volt. But as the input switches from high to low or low to high, our input value will change from ground to VDD. In between this ground and VDD will be having different values, and our substrate current reaches its maximum value when gate voltage reaches near 0.4 times VDD. Actually, we should have a maximum substrate injection current of 100 microampere only for 5 volt of VDD, but it will happen even at 0.4 times of VDD. So because of that, in between itself we will be having some large unexpected current. So since gate voltages are only transiently in this range, as devices switch, the actual power contribution of the substrate injection current is several orders of magnitude below other contributors. So when we switch from high to low or from low to high, in between that transition region we are having only a very narrow region. Only in that particular region we are having this large substrate current. Even though that contributes to static power dissipation, the duration of that static power distribution is very less. So this component of static power, that is static power due to substrate current, is several orders of magnitude below compared to other contributions. The next component in static power is reverse biased junction leakage current associated with parasitic diodes. Normally, this reverse biased junction leakage current associated with parasitic diodes will be in the order of nanoamperes. So as this current is in the order of nanoamperes, this reverse bias junction leakage current also has a very little effect on overall power consumption. Now the third component is due to pseudo-NMOS circuitry. So pseudo-NMOS is an example of ratioed CMOS logic family, in which PMOS pull-up is always on and act as a load device for the NMOS pull-down network. Therefore, when the gate output is in the low state, there is a direct path from VDD to ground and static currents flow. Logic families such as this, which experience static power consumption, should be avoided for low power design. The circuit displayed here is a pseudo-NMOS inverter. Here the static power dissipation in pseudo-NMOS inverter. We'll see how it will happen. Here the PMOS network, it will be always turned on and it will act as active load for the NMOS pull down network. So whenever our NMOS network is turned on, for this inverter, if input is 1, NMOS network is on. So whenever this NMOS network is on, we will be having a direct VDD to ground connection. So that will contribute to static power dissipation. So for normal low power VLSI chips, this pseudo NMOS type of circuits should be avoided. We'll see what are the applications of the pseudo NMOS circuits and where it can be used and where it can't be used. For special circuits such as PLAs, that is programmable logical arrays, or register files, pseudo NMOS circuits may be useful due to its efficient area usage. The pseudo NMOS circuit does not require a P transistor network and saves half the transistors required for logic computation as compared to the CMOS logic. The circuit has a special property that the current only flows when the output is at logic 0. So when the output is at logic 1, all N transistors are turned off and no static power is consumed except the leakage current. So this property may be exploited in a low power design. That is, if you know a signal to have a very high probability of logic 1, say 99%, it may make sense to implement that particular computation in pseudo NMOS logic. But if the signal probability is very close to 0, we may eliminate the N transistor network of a CMOS gate and replace it with a load transistor of N type. So the main three components in the static power are substrate current, reverse bias leakage current, and pseudo NMOS circuits, in which substrate leakage current and reverse bias leakage current can be is of very less importance, and we need to avoid pseudo NMOS type of circuits. Next, we will be focusing on dynamic power consumption. Now, dynamic component of power arises from transient switching behavior of the CMOS device. That is between low and high or between high and low. So we are having an inverter circuit on the right hand side. So if the input is at ground level or at low level, your PMOS will be on and NMOS will be off. So VDD will be connected to the load and output will be having a high level. If input is at VDD or at high level, the PMOS will be off and NMOS will be on, and our load will be connected to the ground, and at the output we will be having low. So while switching from low to high or from high to low in the input state, what will happen? We said our CMOS switches are not perfect switches. So at some point during the switching transient, both NMOS and PMOS device will be turned on, and this occurs for gate voltages between VTN and VDD minus VTP, where VTN is the threshold voltage for NMOS and VTP is the threshold voltage for PMOS. Then, if both the transistors are turned on, a short circuit exists between VDD and ground. A short circuit exists between VDD and ground, and currents are allowed to flow. And this can be kept below 10 to 15% of the total power consumption by keeping the rise and fall times of the all signals throughout the design within a fixed range. Means this happens as your NMOS and PMOS are simultaneously turned on at the transient time, that is at this slope. So if you can adjust this rise time and fall time, we can reduce this power component to 10 to 15% of the total power consumption. And probably this rise and fall time will be made as equal. So thus, short circuit dissipation is not the dominant component of power dissipation in a well-designed CMOS circuit. So the next component is of dynamic power is dynamic power dissipation due to capacitance charging, and it will consume most of the power used by CMOS circuits. It is the result of charging and discharging parasitic capacitance in the circuit. So the parasitic capacitance, the unnecessary capacitance in our circuit. So these capacitance will get charged and discharged. So the power consumption due to charging and discharging of this parasitic capacitance is the main component of the dynamic power consumption. So in this particular circuit, the parasitic capacitance are lumped at the output in the capacitance C. All the parasitic capacitance are lumped to this particular C. So here the input is switching from high to low. So the output should switch from low to high. Okay. So as the input switches from high to low, NMOS pull down network is cut off. NMOS network will be cut off. And PMOS pull up network is activated. So charging the load capacitance C up to VDD. Charging the capacitance C up to VDD. So this charging process draws an energy equal to C into VDD square from the power supply. Now, half of this power is immediately dissipated in the PMOS transistors, while the other half is stored on the load capacitance. That is, from the circuit, C into VDD square power will be consumed. Half will be dissipated in the PMOS and half will be stored in the capacitor. Now, when the switching is in just opposite, that is from low to high, our NMOS will be turned on and PMOS will be turned off. So then half of that power will be dissipated in the NMOS and half will be discharged from the capacitance. So then when input returns to VDD, the process is reversed and capacitance is discharged. Its energy being dissipated in the NMOS network. That is, every time a capacitive node switches from ground to VDD and back to ground, an energy of C into VDD square is being consumed. So this leads to the conclusion that CMOS power consumption depends on the switching activity of the signal involved. Now we will relate the switching activity to dynamic power consumption. Let alpha be the activity, that is the expected number of 0 to 1 transitions per data cycle. F is the average data rate, that is the clock frequency in a synchronous system. Then the effective frequency of nodal charging can be written as alpha times F. This leads to the following formulation for average CMOS power consumption, that is P dynamic is equal to alpha times F into C into VDD square. And this component is the most important one, accounting for at least 90% of the total power dissipation. So in the dynamic power consumption, we need to focus on the power dissipation due to switching activity, that is due to parasitic capacitance charging and discharging. Now we will be focusing on emerging low power approaches, which is being adopted by the industry. So these approaches, it can be divided into 5 layers. So assume the case of a laptop. So most of the laptops now, it can stand up to 7 to 12 hours in battery. So at the system level, we will be having some power saving approaches, something like different power states, like dimming our computer screen when using the battery, then sleep mode, then different partition techniques, etc. So that's at the user point of view, system level. Then at the algorithmic level, that is at the developer level, who develops the code and all, he will be focusing on concurrency, regularity, locality, and complexity of the algorithm. It means the code developed by him or she should run on the underlying parallel hardware or pipeline enabled hardware. It should run and should use all the codes of your processor. So depending on that, the complexity level will change. So all those will be dealt at the algorithmic level. Now this algorithm, it has to be implemented in a particular architecture. So in the architecture, we will be talking about parallelism, pipelining, redundancy, data encoding. All. So in the to get low power approach, we will be doing, most of the times we will be doing parallelism and pipelining. That means at a time we can do multiple processes or multiple threads. Then this architecture, its implementation is done by circuit or logic layer. So how you are going to implement your architecture? That means in the architecture, you may be simply saying your architecture may contain adder or multiplier. So how you are going to implement that adder? For example, calico adder or ripple carry adder. So how you are going to implement that particular adder? So that will be defined in the circuit or logic level. So that logic styles and its manipulation, how you are going to size your transistor, then energy recovery options, all those will come under circuit or logic layer. And all these things are implemented using a particular technology, something like 14 nanometer technology or 28 nanometer technology, whatever technology we are going to use. In that technology node, we will be talking about threshold reduction or double threshold devices like that. So if you reduce the threshold, you can have low power consumption, but your operating frequency will reduce, it will be affected. But if you increase the threshold, you can have high frequency operations, but our power consumption will increase. So that some two extremes are there. So in between we need to manage. Sometimes we may use double threshold devices. So these are the different layers or different approaches for getting low power device as a whole. And ultimately, all will come down to a fundamental set of concepts, saying that dissipation can be reduced by lowering the following points, either by reducing the supply voltage, the voltage swing, physical capacitance, switching activity, or a combination of the above, assuming that we need a reduction in the performance is not at all allowed. Performance reduction is not at all allowed. We need reduction in power consumption. So before winding up this session, we will have a summary of what we had today. We have started with need for low power VLSI chips. Then we have seen mechanisms of power dissipation inside digital indicator circuits. So those mechanisms are static power consumption and dynamic power consumption. So the subdivisions of static power consumption, or the contributors of static power consumptions, were substrate current, reverse bias junction leakage current, and pseudo and MOS circuits. Then we have seen the dynamic power dissipation. So the components were the direct rail connection due to switching transients, then parasitic capacitance charging and discharging due to switching activity. Then we have related dynamic power to switching activity and that equation, that is P dynamic power is equal to alpha times F into C into VDD square. Then we have seen different emerging low power approaches. So that's all for today. Thank you.